finishing graduate student at UC San Diego, and today I'm going to talk about my recent paper on why the direct imaging community as a whole needs to care more about the host star properties. The transit and radial velocity do it pretty well already. So starting off, just a quick intro. There are two major pathways for planet formation: core accretion, in which we have pebbles or planetesimals. They coagulate, and once they coagulate, once you have the core, it accretes an atmosphere to give you a gas giant. And the other is the disk, or the gravitational instability paradigm, which is you have the protoplanetary disk. The sections of the protoplanetary disk can collapse in on themselves, and eventually evolve into planets. Now, the population of directly imaged planets are primarily just super Jupiters and on extremely wide orbits, and neither of the two paradigms can explain the formation of all of these planets. And so we need some way to figure out the formation mechanism. And one very popular way is the C2O ratio. I'm sure all of you have seen this plot like a million times, but just going through it very quickly. On the x-axis, we have the distance from the host star, and on the y-axis, we have the C2O ratio for the C2O ratio in the gas phase and versus the grain or the dust phase of the protoplanetary disk. And what we can see is the gas phase C2O ratio is hopefully this works. Okay, cool. So where is it? Okay. So the takeaway from this plot is the gas phase C2 ratio is consistently above the solar value. So for a planet, a gas giant that accretes an atmosphere after the formation of the core, you would expect the atmospheric C2O ratio to be higher compared to the host star. And for a star formed by gravitational instability, there is no separation of gas versus solids, and it would have a C2O ratio similar to the host star. But is it really that simple? Is C2O ratio as good a formation tracer as we think it is? So here's this plot from Ian Crossfield's 2023 paper, which shows the distance from the host star on the semi-major axis on the x-axis and the various atmospheric abundance ratios, carbon to sulfur, oxygen to sulfur, and C2O relative to the solar values for two different formation mechanisms. One is pebble accretion followed by gas accretion, and other is planetesimal followed by gas accretion. And if you follow the C2O curve, which is the black dotted line, the C2O curve for both mechanisms agree within their uncertainties. But that is not the case for the sulfur-based ratios, carbon to sulfur and oxygen to sulfur, which are an order of magnitude higher for pebble accretion as compared to planetesimal accretion. And which is why it is imperative we move beyond just the C2O ratio, and especially in the era of JWST, where we have been able to detect sulfur dioxide, hydrogen sulfide in a lot of transiting and directly imaged planets. So the goal of the paper was to constrain planet formation by measuring various abundance ratios for the host star, and to look for trends in planet occurrence with host star abundances. And to do this, we measure the abundances for 15 elements, which are all listed here, as well as the carbon to oxygen, carbon to sulfur, and oxygen to sulfur ratios. With the sulfur-based ratios, the host star abundances become particularly important because, as we saw in the previous slide, the enhancement can be like orders of magnitude higher compared to solar. So if you have the wrong sulfur abundance for the host star, then it could throw off your interpretation by quite a bit. And how challenging is it for the directly imaged host stars? So most of the directly imaged host stars, directly imaged planets in general, are as biased to be like pretty young. So the host stars themselves are pretty young. They are more hot. They are hotter, and they are also fast rotators. And so this is the spectra for 51 Eridani, which is an F0 star with a rotation velocity of 70 kilometers per second. And so this is one of the orders with one of the main oxygen features, the oxygen triplet line here, which is, so this feature is supposed to be like 3 oxygen lines and not just 3 oxygen lines. If you actually go in and look at how many lines are there, you have like 9 lines or 8 or 9 in this just one blended feature. And to get the abundance of oxygen, you need to sort of devolve all the sort of effects of all of the other lines on the equivalent width of the feature, or yeah, on the size of the feature basically. So I did this analysis for 5 host stars, HR8799, very well-known multiplanetary system, HD984, 51 Eridani, which has one of the lowest mass directly imaged planets, GJ504, which has the second coldest directly imaged planet, and HD206893, which is another multiplanetary system. And the spectra for all of this was obtained using the Levy spectrograph at APF, which is optical spectrograph with a resolution like of 120,000. And the analysis I did for the abundance measurement was a 2-part analysis. First part was a forward modeling analysis, which involved finding the basic stellar parameters, and then using the basic stellar parameters I obtained to get a custom grid with varying carbon and oxygen, which are then used to determine the abundance values. So doing the forward modeling for one of the host stars, SD206893, this is how the spectral fit looks. So in this, we only fit for the region around the oxygen feature, which is right here. And the spectra mostly fit very well in that region. And this gives us a spectral fit C2O ratio of 0.81, which is supersolar at 2 sigma. And the other method was using the equivalent width, which is, I'm sure most of you would be familiar with it. Continuum normalize the spectrum, measure the area under the spectral line, which is effectively your equivalent width, and using the spectral analysis software Moog, I converted the equivalent width to an equivalent abundance. And I did this for carbon, oxygen, and a lot of other elements, and this gives us an equivalent with C2O for 0.69 for this star, and which is 1 sigma, which is solar at 1 sigma, within 1 sigma. And if we look at the C2O ratios, and as well as the carbon to sulfur and oxygen to sulfur ratios for all 5 targets, for C2O, we see broadly solar compositions, except for HD206893, as I highlighted earlier. But if we go to equivalent width, broadly solar. And carbon to sulfur and oxygen to sulfur are also broadly solar in general. But with the C2O ratio, you would notice that the equivalent width C2O ratios are at least a factor of 2 greater than the one measured via equivalent spectral fitting. This is obviously because the high rotation velocities, which makes it difficult to sort of remove the effects of all of the other lines within the big blended feature. And another thing I did was to look at the abundance trends of all 15 elements relative to solar values for all 5 stars. So here we have, at a glance, what we see is HR8799, except carbon, oxygen, all the other elements are subsolar, and which we kind of expect because HR8799 is a lambda boost star. It has anomalous photospheric abundances. And the other thing which was interesting was for GJ504, GJ504 has supersolar compositions across for almost all elements. And the idea behind this plot was to look for any systematic deviations in the abundance of a particular element relative to solar, which might indicate some kind of chemistry in the protoplanetary disk, which is specific to wide orbit Jupiters. And so far, we do not see anything. And eventually, I would like to do this for all directly imaged planet host stars. And now that we have the host star C2O, let's compare it to the companion C2O values. So these are all the most of the companions have C2O values in literature, and all of these agree with the stellar values at a 1 sigma level, except GJ504b, which agrees at 2 sigma. But of all of these, GJ504b, 51 Eridani b, HD206893b, and 51 Eridani b, all three have their C2O measurements only using ground-based photometry or low-resolution spectra from instruments like GPI or SPEAR or Gravity, and which is why there are ongoing JWST programs for all three of them. So for GJ504, there's a GTO program, which I am leading the analysis for. 51 Eridani has a Go program, which I am a co-I on. And 206893b has a Go program for which I am the PI. So I'm going to talk more about my JWST program. And so HD206893b. So the question with this was, is it a planet? It's 28 Jupiter masses, which makes you think no. But it is located inside a debris disk, and it has a coplanar inner companion. And both companions are coplanar and with the debris disk as well, which strongly suggests this might have formed via a planet-like, which it might have a planet-like formation mechanism. And so far, so the goal behind this program was to see if the 13 Jupiter limit that we use to distinguish between brown dwarf and exoplanets, does it really actually make sense? Like, are there the other formation tracers, for example, sulfur-based formation tracers, which is the main motive of the program, to get the sulfur abundance in this companion, if we can use sulfur-based formation tracers to distinguish between the lowest mass brown dwarfs and the highest mass exoplanets. And this was observed using JWST in October 2024. And I'm still currently working on the data reduction and analysis, but I hope to have updates by later this year. And yeah, this is the takeaway from my talk, and I'll take any questions.
Great. So any questions for Anish?
Andreas Quirnbach, Heidelberg University. Regarding your last point about distinguishing quote-unquote planets from brown dwarfs, taking the mass definition of the boundary makes sense from a classification and nomenclature point of view. But of course, planet formation doesn't know anything about nuclear physics. So the formation processes may rather be overlapping this definition. In that context, it may be more useful to take the mass ratio between the planet and the star, because we see what is typically known as the brown dwarf desert also depends on the stellar mass. So if you take a companion population that you think formed in a binary star formation process, then this mass ratio may be a better definition. And there are clearly objects that formed in a disk. We have published a paper on a system that has 2 brown dwarfs with about 20 Jupiter masses in a 6-to-1 resonance. And you can get in that resonance almost only by forming in a disk. So that is very clear evidence that these objects formed in a disk, although they are above this 20 or so Jupiter threshold.
Yeah, so that is one thing we would explore, like doing mass ratios, but yeah, we wanted to see if there is a sort of abundance manner as well, since, I mean, so far we have not conclusively seen anything being like a definitive formation tracers between various mechanisms.
Dan, and then across Jones.
Dan Huber, Hawaii. This is a really nice talk. Thanks for doing this systematically for the directly imaged host stars. I think this is long overdue. It's great to see. I have a question about the V sin I problem, right? So you talked about the rapid rotators. How rapid can they be before determining the abundances just becomes too difficult? And a related second question is that some of these stars are A stars and they pulsate, like HR8799. And does that affect your abundance analysis, the pulsations of the star?
So currently I am trying to measure one of my projects is measuring the abundances for beta pic, which is A6 or something, early to mid A, and it has a rotation velocity of like 120 kilometers per second. So at least for carbon and oxygen, it seems possible. An equivalent width analysis might not be feasible for that, but yeah, I'm still exploring. But carbon and oxygen, at least I feel I could get them. Yeah.
Maybe a very quick question on Zoom.
For GJ504, did you correct your oxygen abundances for non-LTE conditions in its photosphere?
So for GJ504, we used one spectral line, which at least from the Amarsi paper, I did not see it has. So the corrections that we would need for like non-LTE effects is sort of dependent on line by line. So the specific spectral line that I use to measure the oxygen abundance, the oxygen triplet, at least from the paper I noticed, did not have LTE corrections required. And in general, I expect the LTE corrections to not be as important as the errors in the measurement themselves.
Okay, and with that, let's thank Anisha Dan.